Hello everyone. I am very pleased that WLIA invited me to give a virtual presentation. My presentation today for the 2020 WLIA Virtual Spring Regional Meeting is on 3D laser scanning and building information modeling, or more commonly referred to as BIM. To demonstrate the potential of BIM, we will explore the Hartsfield Jackson Atlanta International Airport Terminal project, one of the busiest airports in the world. This presentation will identify the equipment used, scanning methods, locations within the terminal where scanning occurred, and some of the potential end products for this project. This sample project was very complex in planning and execution, but provides a comprehensive look at how a BIM project is completed from initial scanning to a final work product that can facilitate airport facility management and day-to-day operations. But before we explore the benefits, specifications, and deployment of BIM, I want to briefly tell you about GPI. GPI Geospatial is a division of Greenman Peterson, Inc., an engineering company located on the eastern seaboard of the continental U.S. Our axiom is GPI, many talents, one firm. GPI Geospatial is a multidisciplinary geospatial firm. Our services include 3D high-definition laser scanning, building information modeling, aerial photography, aerial LiDAR, mobile LiDAR, surveying and mapping, photogrammetry, asset inventory and management, GIS applications, and emergency response. All of these service areas can be completed with assets owned and operated by GPI Geospatial. Our staff of highly trained technicians have completed thousands of projects over the past years spanning all of these disciplines. Who is GPI? GPI is licensed to operate in 20 states. We have 46 years of geospatial experience. Our headquarters is located in Orlando, Florida, and we are a full-service mapping and 3D modeling firm. Our staff includes 16 licensed surveyors, 4 ASPRS certified photogrammetrists, and 20-plus LiDAR specialists. GPI Geospatial has 9 offices in 6 states. Our headquarters, as previously indicated, is in Orlando, Florida, but we do have a regional production facility in Sheboygan, Wisconsin, with 13 employees. The Sheboygan office is a location I work out of and conduct my business development activities. Since the Sheboygan office was opened, we have completed or are completing projects for a variety of clients in the upper Midwest, such as Wisconsin DOT, Sheboygan County, Wisconsin, Ramsey County, Minnesota, and many private engineering and surveying firms. The topics of this presentation include an introduction to BIM, a general project workflow, LiDAR extraction methodology, airport terminal levels that were scanned, visualization capabilities, asset facility management, GIS integration, benefits of BIM, and a presentation conclusion. We will explore these topics to provide a better understanding of how BIM is deployed and the significant benefits of a BIM program. What is BIM? The industry definition of BIM is Building Information Modeling, or BIM, is a digital representation of a facility's physical and functional characteristics. It can be shared by architects, planners, engineers, constructors, operators, and maintainers to provide reliable 3D information for decision-making throughout the facility's life cycle. BIM can be as simple or as complex as a client requires. Understanding the end users, their needs, and how they will use BIM on a day-to-day basis within the confines of facility management will define the requirements for scanning acquisition, post-processing, and the final complexity of the BIM product. This slide depicts the comprehensive and complex virtues of BIM, where all HVAC, water sewer lines, electrical, and communication infrastructure is captured and classified to support facility management activities. A myriad of BIM software packages are available to model reality spaces from LiDAR scan data. Some of the more popular packages include Autodesk Revit, Autodesk BIM 360, SketchUp, and Vectorworks. For the purpose of this presentation and the project example, Autodesk Revit was used for the BIM processing. The list of software is increasing as the value of BIM is becoming more recognized in the architect engineering community. The American Institute of Architects, or AIA, has adopted a series of standards for BIM modeling. These are called levels of development, or LODs. The most rudimentary level of development is LOD 100. Model elements may be generically represented in the model with a graphic symbol or other similar feature. Information related to the model element can be derived from other model elements. This LOD is the most simplistic and base level. The level of detail is held to a minimum to create a generalized element that describes a feature in the space with few and nominal characteristics. This LOD is best used in initial conceptual design of a space, which will be refined upon approval of abstract architectural concepts. Next is LOD 200, General Model, which is the second level of development. The model element is graphically represented within the model as a generic system, object, or assembly with approximate quantities, size, shape, location, and orientation. This level starts showing some features and dimensions of the element, but excludes any infrastructure within the element. Here the model shows additional features that were not included in LOD 100, but does not include the complex systems that can be incorporated into the element structure. Next is LOD 300. Accurate model is the third level of development. The model element is graphically represented within the model as a specific system, object, or assembly in terms of quantity, size, shape, location, and orientation. With this LOD, additional features of the element are refined and become more evident. Exterior unique design elements become part of this model, depicting what the model would actually look like in the real world. This lends to a more realistic view of all of the elemental models within the space. Next is LOD 350. Accurate model, including building elements, is the third intermediary level of development. The model element is graphically represented within the model as a specific system, object, or assembly in terms of quantity, size, shape, orientation, and interfaces with other building systems. This intermediary level shows not only the graphic exterior details of the element, as with the previous LOD 300, but includes the primary internal infrastructure systems that are functioning within the element. Although internal systems are depicted, they are displayed in a general manner with limited details of the assembly or installation of the element. Next is LOD 400. Accurate model, including specific assemblies, is the fourth level of development. The model element is graphically represented within the model as a specific system, object, or assembly in terms of size, shape, location, quantity, and orientation, with detailing, fabrication, assembly, and installation information. At this level, not only is the element accurately represented, but all internal components are modeled in significant detail. Each feature and system is displayed in finite detail, providing a better and more detailed understanding of how individual systems function and how multiple systems share and work together within the element space. The final and most detailed level of development is LOD 500, As-Built Facilities Management. This level will have suitable geometry and information to support operations and maintenance. This level is typically field verified, flexible to meet facilities management workflows, and incorporated into airport operations. Since this is the highest LOD level, all architectural features, systems, and assemblies are included in the space. Windows, doors, gates, stairs, escalators, HVAC, fire, electrical, internet, and connective systems are incorporated. Even seating, tables, and indoor planters are part of this comprehensive detail. This is the level of development which was utilized for the Hartsfield Jackson Atlanta International Airport. BIM projects are complex and require extensive planning built into a project workflow. This starts with a collection plan, which includes a review of the floor plan for each level, an initial walkthrough to define scanner placement, and the challenges operators will face during collection. The collection plan is then implemented with the scanning imagery collection phase on site. Once the data is collected, the LiDAR is processed to index the point cloud to control and to sync the color imagery to the point cloud for the creation of a colorized point cloud. After the controlled and colorized point cloud is created, feature extraction can begin. Approximately 65 to 75% of features can be extracted through automated methods, but manual extraction and editing will need to be used for the remainder. During the feature extractions, some elements will require a physical walkthrough to determine the purpose of the specific element or elements. Leaving the unknown elements until feature extraction is complete will minimize the physical visits required to complete accurate classification. The final step is to begin modeling the 3D surface and features in a software environment such as Revit. This can be one of the most complex steps in the workflow depending on the required LOD level and the end user requirements for the BIM project. The 3D scanners deployed for BIM by GPI Geospatial are the Riegl VZ400 scanners. Two scanners, one a VZ400 and the other a VZ400i, were utilized for the static scanning at the Hartsfield Jackson Atlanta International Airport terminal. The image on the left displays a scanner mounted on a tripod similar to our deployed units at the terminal. The right image is a close-up of the scanner with the high-resolution digital camera mounted on the top. The camera requires imagery during scanning sessions that we use to colorize the scan point cloud to facilitate feature identification in the BIM modeling. Now, let's go over some of the technical specifications of the Riegl scanners. The Riegl VZ400i has a variable pulse rate of 42,000 to 122,000 measurements per second with a variable collection range of 0.5 meter to 600 meters. This permits variable point collection densities depending on the size and complexity of the structure being scanned. The Nikon D810 36 megapixel camera mounted on the top of the scanner provides simultaneous image collection to facilitate colorized point clouds. Let's delve into the point cloud data. As a result of scanning, a point cloud is generated. A point cloud is a collection of points with known X, Y, and Z values. The point cloud can have sparse spacing, approximately 1 or 2 points per square meter, or dense spacing, approximately 200 to 1,000 points per square meter, depending on the application and methodology used. In the case of BIM, these points are at the higher end and are very dense and physically represent walls, stairs, hand railings, electrical boxes, and a whole variety of features in the space being scanned. In order to tie individual scans together and to a baseline survey, GPI surveyors set multiple 10-centimeter targets on tripods to establish points on the floor. One of these target tripods is shown at the base of the steps in this colorized point cloud. These targets will show up in multiple scans and allow individual point clouds to be stitched together with ties and orientation in the same coordinate grid. The final step is to register high-resolution color imagery to the point cloud to facilitate the downstream feature extraction. LiDAR scanning can capture not only interior but also exterior features. This is important since not only do interior spaces have building information, but exterior facades include drive approaches, lights, signs, utility structures, and are the first thing a traveler sees when they drive or walk to a public or transportation building structure. It is easy to envision BIM as just interior room scans, but the exterior of a structure can be intricate and just as important. The point cloud is geographically accurate when tied to a baseline survey in a known reference frame, and when deployed with sufficient targeting, provides room-to-room connectivity. LiDAR scanning captures incredible detail, allowing for accurate modeling of a feature's shape, size, and location, to name a few attributes. The acquisition phase is non-intrusive with minimal impact to the traveling public and facility staff employees. The operators can even collect during AM hours and low-volume timeframes to minimize disruptions at the site. The majority of our scanning operations at Hartsfield Jackson Atlanta International Airport were completed from midnight to 7 a.m. in the morning, and with proper execution, LiDAR scanning leaves no trace on the project site. Previously, I referenced the 10-centimeter target. The image on the left shows this type of target set up on a road corridor. The 10-centimeter target is set up in multiple areas to tie the scan data to known baseline control and to stitch together individual point clouds from multiple adjacent scans. At the base of the tripod, the spear right above the T in the word target on the left image, a small target is set, such as the paddle target shown in the right image. Many different types of paddle targets are available for this purpose. The paddle target permits the surveyor to revisit and reestablish a 10-centimeter target on a tripod at a later time if additional scanning is required. The next slides depict scanning positions with targets set for control. Each position of the scanner is carefully determined and becomes a component of the collection plan. Now, let's review some of the scanning locations within the airport facility. Here, in the left image, you can see the LiDAR scanner collecting data in one of the underground train stations. The three inset images on the right depict, in a larger view, the 10-centimeter target tripod in front of the train door, the paddle target at the base of the 10-centimeter target, and the removal of ceiling panels to allow capture of overhead and hidden utility structures in the suspended ceiling. In an airport facility, the vast majority of HVAC, electrical, plumbing, and communication infrastructure traverse through the cavities and suspended ceilings, so it is vital to remove ceiling panels to expose and capture these features in each and every scanning session. In this instance, on the left image, the scanner is set up in a hallway with light to moderate pedestrian and airport staff traffic. Again, you can see in the insets to the right the 10-centimeter target set in the hallway, but because this is a hallway frequented by foot traffic, the targets were shielded by bright barriers to ensure that no one accidentally hits or trips on the tripod and disrupts the control point. Such accidental incidents can create problems for the scanning technicians and need to be identified and addressed in the collection plan to ensure each scanning session is completed with minimal pedestrian interaction. As with the first position, specific ceiling panels were removed to allow the critical infrastructure above the suspended ceiling to be scanned. Finally, the left image depicts the scanner set up near the base of a series of escalators. The inset on the top right shows the series of 10-centimeter targets set up for this scanning position. How many 10-centimeter targets do you see in the top right image? If you said 5, you are correct, although the target tripod in the foreground on the far right is partially blocked by the vertical support structure. You'll also note one 10-centimeter target is placed at the bottom of the escalators, and, unseen in this image, a second 10-centimeter target is set at the top of the escalators on the upper level. This was critical to ensure a solid tie between the scans on the different levels of the airport terminal structure. Finally, the lower right image conveys the ceiling panels removed to capture the above hidden infrastructure features during each and every scanning session. Here we see another 10-centimeter target in a colorized point cloud in one of the utility rooms. Every scanning session required careful placement of these 10-centimeter target tripods. The collection plan detailed all placement of these tripods in the airport level and structure. Now, let's look at a cross-section of all of the scanned areas that were included in this program. This slide displays the full terminal area that was scanned with all levels in a horizontal view. The entire terminal scan area includes 151,000 square feet. Individual sublevels will be displayed as 3D oblique representations, one at a time below the upper terminal horizontal view as we progress through this slide. The first level is the boarding area highlighted red on the upper horizontal view. This area encompasses approximately 16,000 square feet. This is the primary pedestrian traffic area with a myriad of vendor services and unique architectural elements. This level involves some of the most difficult challenges for the scanning technicians due to the sheer volume of pedestrian airport personnel traffic. The second level is the apron area highlighted green on the upper horizontal view. This area is approximately 60,000 square feet, including parking lots for employees with heavy mechanical and electrical elements. Now look closely in the center of the apron level oblique view at the bottom. A red rectangular box will appear in the center of this level. This was a room that was previously unknown to the client. LiDAR scanning is a useful tool to document assets in space, especially when outdated as-built or no plans are available for engineering design. The third level, displayed in lavender on the upper horizontal view, is the mezzanine and ATGS areas covering 75,000 square feet. The mezzanine includes employee TSA check-in with a variety of architectural elements. The ATGS includes mechanical and electrical rooms and a train boarding area. The 75,000 square foot apron level includes an employee parking area and consists of heavy electrical conduit, HVAC, plumbing, lighting, and architectural elements. This level took the longest time to model due to the sheer amount of electrical and mechanical utility elements in dark areas. The displayed image is the actual colorized point cloud from the on-site scanning. You'll notice the 10 centimeter target tripod in the foreground. In the raw LiDAR scans, these targets will be seen in multiple locations. We have now transitioned to the Colorized BIM model. This was created using Revit and permits a 3D rendering of all physical elements on the apron level. Upon completion of the BIM modeling, VR was created to enhance the visual content and for a more immersive experience. Shading, sun perspective, colorization, and other enhancements make the VR model look realistic. The architect-engineer can use VR to determine feasible changes and upgrades to the space. Further, the architect-engineer can see if elements are blocking in addition to the space without being physically there. This is an extremely useful tool for the client to understand design intent and opens communications between client expectations versus engineering design. Options, upgrades, and scenarios can be explored, evaluated, and incorporated without personnel visiting the site. This short video will pan around the VR image displaying the piping, conduit, structure, and facilities. One of the most important features of BIM creation is the ability to create visual walkthroughs directly in Revit for a portion or all of a floor level, such as the airport mezzanine level. This feature allows the architect-engineer the ability to visualize potential changes needed immediately. It can also identify potential problem areas, such as restricted pedestrian traffic flow, airport staff station concerns, and bottleneck entrances and exits. One can also create indoor routing directions, which are critical to assist pedestrian traffic to a variety of locations within the airport terminal. Let's take a BIM walkthrough of the mezzanine level. You can see the gates, escalator, TSA check-in, and walk-through metal detector for the airport employees. Once again, all physical features are represented to permit the architect engineer to create upgrades, modifications, and/or repairs to the level without having to visit the site. This feature alone can save thousands of dollars on repeated site visits to determine a previously unidentified feature or features on the level. Further, multiple engineering and architectural firms working on the project can see and share data to coordinate modifications and changes to the space. Now, let's take a BIM walkthrough of the ATGS level utility room. This walkthrough was created using the LiDAR scan data with Revit software. You can see the HVAC, piping, and electrical boxes and conduits among a variety of other elements. Each element in the BIM model can be colorized, shaded, and represented in the physical space. With an attached database, attributes can be assigned such as flow rates, installation dates, electrical line type, previous upgrades and or repairs completed, and scheduled replacement dates. All of these features can simplify facility management services by allowing maintenance crews the ability to evaluate problems and determine solutions from a remote location. Automated tools such as smart tracing, which uses LiDAR intensity imagery features in conjunction with viewing of the co-registered imagery, accelerate the creation of complex elements. Smart tracing allows the extraction operator, for example, to trace individual pipes from the beginning valve junction to the end of the pipe assembly automatically. Revit standards created by the AIA and modified to client requirements create consistency in data creation. Finally, 3D LiDAR scanning permits the creation of LOD 500 datasets. Revit models allow an immersive view of the infrastructure data from several perspectives. Revit also provides, for example, pre-made architectural elements that can be incorporated in the modeling, such as walls, floors, ceilings, doors, and windows, to name a few. Each of these pre-made features hosts a series of attributes for customization to represent the feature in the real space. The flexibility and ease of use of Revit is the true power of the software. Once the Revit model has been created, as shown in an earlier slide, shading and colorized effects can be applied to make the scene elements look almost realistic. BIM models are used for a variety of purposes. Visualization to view individual components or complete assemblies within a given space or level. Visual scheduling to compare a baseline construction schedule to the real-time construction level. Asset management to determine the current operation, location, and life expectancy of individual components or complete assemblies in the space. 3D printing permits physical models to be created that represent the actual design in the model. We've seen the visualization capabilities of BIM in the walkthroughs of the mezzanine level and the ATGS utility room shown on previous slides. All visual content in this presentation uses examples from the Atlanta Hartsfield Jackson International Airport project. BIM models can be exported to review software such as Navisworks for construction simulations. This allows the user to link model elements to temporal data such as a predetermined baseline construction schedule. The following video will depict a simulation of a baseline construction schedule, screen left, in tandem with an actual construction schedule, screen right. This type of contrast provides feedback on staging conflicts and potential setbacks in the schedule. This is a crucial dynamic to determine whether a construction schedule, especially when it spans years, is ahead of schedule, on track, or behind schedule. In the latter case, adjustments to crews and assets would be required to bring the schedule back in line with the baseline schedule. Another feature of visualization is class detection, detecting elements that intersect, for example, a beam running through a wall or around a buffer tolerance. For asset management, the data is smart, not just a series of points, lines, and polygons. In this short video, you can see how a single or multiple pipelines can be visualized or traced from beginning to end. This facilitates conflict detection in infrastructure. Elements can be tagged with an ID for direct linking to asset databases or in field systems. This short video depicts how critical support systems can be status checked for nominal operation. These element links can be structured to determine performance measures and degradation curves involving service life and for budgeting and forecasting. Let's talk about GIS integration of data. Because of this level of connectivity, airport information can be integrated into existing GIS databases across all platforms, creating intelligent connectivity from landside to terminal, gates, and airfield. Physical assets can be tied to land assets and general uses, and the entirety of the system is fully customizable to tailor to a client's needs. 3D printing is used for creating models. For example, using the BIM model, a physical scale model can be created of the boarding area through 3D printing. This 3D model is at a scale of 1 inch equals 215 feet. 3D printed models can be used to show scaled physical models of a design, similar to architectural models. Models are easily reproducible and are highly effective in showing clients' design intent. This model was used in a presentation with Miami Airport to showcase the current boarding area in the Atlanta airport and create a discussion about future renovations in the Miami airport space. This short video will play to view the 3D printer in operation. There are many benefits of BIM modeling. According to a report from McGraw-Hill in 2012, airport BIM users reported a return on investment over 25%. Among the many benefits of a BIM solution, preventive versus corrective maintenance, reduced cycle times for project workflows, improved visualization, full life cycle operational cost benefits, fewer unplanned design changes, fewer disruptions in the construction process, linking of digital information, collaboration across multiple teams using a single source of information, space management, fabrication, planning and analysis. The largest benefit for the project design phase is reduced errors and omissions in construction documents used and class detection, spatial coordination during construction. And in the life cycle operations phase, facility building performance was improved, optimizing facility operations and maintenance, and using an as-built BIM as a database for rooms, equipment, spaces, etc. This will be the last piece of information I present and is not related to the airport project. Our technicians scanned a hometown church in Tampa, Florida. This walkthrough video is a little long, but depicts raw scanning of the interior of the church. This is a perfect example of raw data collection. You'll see ghost images of the 10 centimeter targets and the technicians in multiple locations as they are progressing the scanning operations through the different rooms in the church. The 10 centimeter targets and personnel data points, along with all non-facility features, i.e. chairs, tables, etc., will be edited out of the point cloud in the post-processing phase. Fire extinguishers, smoke detectors, and first aid kits mounted on the walls are all visible in their true location within the church. Colorful signs and posters in the kids zone are easily readable. You'll also see two transitions between floors. This point cloud was colorized using imagery acquired with a Nikon camera mounted on top of the scanner. Thank you for listening, and I hope you enjoyed this virtual presentation on building information modeling, or BIM, and can take away some informative and new concepts on this emerging technology. Feel free to contact me with any questions that arise concerning BIM and its implementation.